my slide?
Yes.
Okay, so perfect. So I will just begin, right?
Yeah, you can go ahead and start your presentation. Thank you.
Okay, so as already introduced, we are giving a talk on Bautista-DA, which is a framework for doing large-scale elastic and fault-tolerant ensemble-based data assimilation. I'm going to give this presentation together with Kai, who is speaking on particle filtering with our framework in the second half of the talk, and I will introduce you to how we did ensemble-Kalman filtering on a very large scale, so with more than 1,000 members, and how we optimize the performance of this. The project actually is a collaboration in terms of the ECHO 2 project. It's the Energy-Oriented Center of Excellence. That's what ECHO stands for. And we work together with people from Barcelona Supercomputing Center and from the Juelich Forschungzentrum. And yeah, myself and Bruno Raffin, we are from Inria, and we are also involved in this project. I will jump directly into some technical details because we have only very few time. There were already quite some frameworks for data assimilation presented today, and most of them were doing what is called offline data assimilation. So you are launching the tasks that do your propagation, that are normally instrumented model codes or just the model itself, and those then write the background state data to some persistent storage, be it the SSDs on Fugaku or some parallel file system. When you got all the members propagated, you start another task, another job that is loading the data back from there, and that is doing the update phase, calculating the analysis states using the observations, and you write everything back to files and start the next round of member state propagations. And obviously, file systems do not scale as well as we scale, or do not get faster as compute speed gets faster. And so you get slowed down a lot on very large scale by this. And though the idea came up to do online workflows, and there was already some existing frameworks that are supporting this. For example, PDAF is a very good example. And here you are running the propagation and the update phase in the same application. Everything is one monolithic code, and you are exchanging the files not via the file system between those parts, but via MPI connections, for example. And the two of them have different advantages and disadvantages, and I picked the ones where our framework will give very good results here. So, for example, offline workflows doesn't avoid the high pressure on the file system, while online frameworks do. The problem of online frameworks is that if you have member propagations that take a very different amount of time, often you have to wait for the last member propagation to finish before you can do your Ensemble-Kalman filter update step. And this means you get quite some load imbalance. But if you run it offline and every member propagation has its own job on the supercomputer, you will not pay for waiting, for idling model codes that wait for the next analysis state to be propagated. Another thing that doesn't work so well with offline workflows, since you are restarting your model all the time, you might have some models where the initialization, the startup of the model is actually quite costly. And so you can avoid this using online models. But at the same time, online models have a problem especially if they are implemented using MPI, that if there's one member propagation that numerically fails, that you have to restart everything often, because the most MPI applications are not implemented in a fault-tolerant way, and I know it's also quite challenging to do this with MPI. And we want to tackle all those issues with our framework that is called Bautista-DA. Bautista actually is a family of frameworks that started doing iterative statistics in a Monte Carlo ensemble-based manner, and now we tuned it to be able to use the same techniques for data assimilation. How does this work? The key feature actually is what we call member virtualization. That means we take existing simulations that you want to use for your data assimilation. We instrument the code in a way that the simulation doesn't get the input data, the analysis states from the disk anymore, but rather gets it over network from a central point, and then also does not write back the background states to the disk, but sends it to the central point. We work, the central point connection isn't an MPI connection, but rather something very dynamic like TCP. And we also do data redistribution, so the parallelization of those simulation codes can be quite different from the parallelization on the central point. The central point is a parallel server, so they are really the same connections that you use like when you connect to a website. And this parallel server is basically connecting all the different state parts from all the members and from all the runners that are the instrumented simulations code you saw on the previous slide. And each time a runner sends a state, background state, the server tries to answer directly with a new analyzer state that needs to be propagated. Obviously, sometimes it cannot because it's waiting still for the last runner to finish the last member of one from a simulation cycle. And then the server basically does the update step. We are largely relying very thankfully to Lasniger's PDAF implementation here, because so we can use a manifold of different data assimilation schemes to actually perform the state update. And then we are sending out the next set of analyzer states to the runners. We start all those things in different jobs on the supercomputers using a launcher. That is another component in Melissa distributed application run. And this launcher basically submits all those simulations as parallel runners and a server job. And the simulations, the parallel runners, then connect to the server and ask it for states to be propagated and send the resulting states back. And if the server got enough, yes, it does the assimilation updates using observations. If one runner crashes, the launcher will try to restart it, but actually the application could even run further with one few runner, because the server will then just see that the state propagation didn't finish successfully and will schedule it following the list scheduling algorithm to the next free runner. And to give you some ideas what performance improvements can reach with this, you can see that on the very small scale, with 250 up to 1,000 members, we are maybe compatible, but the advantage that you get from this kind of load balancing is not that important. While on the very large scale, we experienced a lot of improvement, and this is even stronger if we do state output. If you use the standard way of our model, in this case we are running the path flow model on the Neckar catchment with a rather small state size. But if you use the standard way of outputting all the model data every time step, this produces large pressure on the file system, leading to a lot of load imbalancing. And if you don't have a framework that tackles this load imbalancing, you will just waste a lot of compute time. And so, yeah, you can really see that this way of doing things gets very important when you go to the very large scale. And this is for ensemble Kalman filters. And now Kai will jump on particle filtering, because there you can do quite some more optimizations. So I would pass the screen share to Kai. Don't know. Kai, are you there?
Yes, I'm there. So I thought that you would continue with the slides, but
sorry. Okay,
no, no problem. I just opened the slides here, and then it's easier for me. Okay, I'm going to share now. Okay, can you see this the slides?
I can see it.
Okay, perfect. Good. So yeah, I will be introducing the particle filter implementation in Melissa DA. And basically we have three assumptions here. The first assumption is that the particles do not change during the resampling. Then the second one is that the weights of each of the particles can be computed independently from all the other particle states. And that the third one is that the resampling depends only and merely on the float or double weights of the particle filter. And what we need to do is propagating the particle from T to T prime, where T prime is the time where we want to apply the filter. So we need to update the climate model with the input state, run the climate model to get the output state. After that, we need to compute the weights. So essentially compared to the observation to assign the magnitude of the weight. And at the end of each cycle, we need to generate the probability density function to resample or sample new particles from that. So essentially what that means is normalizing the weights at the central point. The first two tasks will be executed running the climate model on the runners that Sebastian introduced before. The third task is produced on the server. And the first two tasks, obviously, we have to perform p times, and the third task only one time. And take into account the assumptions, what we did, the third assumption that for the resampling process, we only need the weights, gives one important performance increase here, that we only have to circulate the weights in the system. So only an array of floats, essentially, between the runners and the server. The strong point of this implementation is that what Sebastian also already mentioned, that the runners are essentially adaptable to the problem size, so the number of particles and available resources. Then the components are completely separate, so no shared MPI domain. So every component, the runners and the server, run on separate jobs, actually. Then the computation takes place between the components over TCP, the network, and that leads to the feature that the components can fail without affecting any other resources, and the launcher takes place of relaunching them. Then we have for the particle filter a local a particle cache on the local storage that enables particle state prefetching. So for the future propagations of any particle, the server knows that the particle needs to be propagated. We can already preliminarily load this state to the runner so that it can immediately start with the propagation when it's its turn. And that is also taken into account by the scheduler in the server. The architecture is essentially the same as it was in the Kalman filtering of DA, Melissa DA. So we have the runners, we have the server, and we have the launcher that wraps everything together. The runners run the climate model, implement the API of Melissa, and here there starts the difference, because under the hood, all the things that happening are completely different to the KF case. The API maintains the weighting of the particles, so the user has to apply supply a calculate weight function, and we calculate the weights on the runners. The runners implement a particle cache. The server takes care of the particle scheduling and the particle resampling. And since it has global knowledge of all the other runners' particle cache contents, it also maintains the prefetching and the eviction of states.
Sorry, 2 minutes left.
Okay, perfect. And I just want to show the experiment, what we did on Fugaku. So we have experiments with WRF on Jonsei and one with the dummy model on Fugaku, a bigger run on 512 runners with 4 nodes per runner and HDB state, 2048 particles. We can see here the trace of 64 selected runners, and I will go a little bit faster through this. So we have a trace of one randomly selected runner here. So we have the weight calculation and we have the propagation, which essentially contribute to the actual computations that we have to do. And we have the idle times at the end of the assimilation cycle and the load and store operations to the cache, which are essentially the waste. And we have the load and state of the PFS, which is taken on by a dedicated process that runs on every of the runners asynchronously to the operation of the climate model. And we can see that in 6% only, we need to fall back to the parallel file system, because thanks to the prefetching, in 94% of the cases, of cases, the particle state is already local on the node, and we can immediately go on with the propagation of the particle. So we have, to conclude, we have ported to WRF the particle filter already. We tested it on Fugaku, and we are working on a speculative scheduling to improve the load balancing at the end of assimilation cycles. And we want to port to NICAM. After that, perform large-scale experiments. And we have some feature what we haven't activated yet because we didn't see any improvement there now. But we assume or hope that on large-scale experiments, this will change to exchange particle states, not through the PFS, but rather through a P2P network from other runners that can provide this state. And that's it. So let's get in touch when you're interested, or questions if you have some. Thanks.
Thank you, Kai and Sebastian, for the very interesting talk. And let's move on to the question. I now have, okay, there's one question from Lars. I'm going to read it. He says, nice work. Regarding the particle filter implementation, computing the weight is usually a cheap operation. Thus, what do you gain in performance when you still need to communicate all particles between the server and the runners? Is it just that you need to communicate not all M particle, but only a subset?
Yeah, so the thing is that we don't have to collect the particles on the central point. So this is the first big advantage that we have. So we don't have to send all the particles to one point to do with an assimilation. And then the calculate weight operation also might be quite expensive when you have to transform when you have a very expensive observation operator, for instance. And what we see is that comparing to the common filter case, that we have a very high parallel efficiency, and because we can parallelize essentially all the individual operations, and then the resampling step is very short. So that is the advantage.
Maybe I can add one thing. We are basically only sending the weights, so one double per particle to the central point, and all the states, they are cached locally with those different cache hierarchies, and then only if you need to shift them, if you need to move the particles to another place to parallelize the propagation for the next cycle more, then only we move some particles around, but otherwise we do not do this. So, yeah.
Okay, thank you very much. I think it's time to move on to the next talk. And thanks again. You can stop sharing your